are the questions, problem set on thermodynamics, and I guess I'm having to do it at the last minute, and I'm not going to put a lot of explanation on this. I just want you to see how it's been worked out. So A is the isothermal expansion. And B is a change at constant pressure, while C is at constant volume. Ten to the power 5 is approximately 1 atm in pascals. And you got to change milliliters into meter cube, so that's why there's 10 to the negative 6. Net flow into the gas, 78 joules. Temperature's got to be in Kelvin again, so T1 and T2. And if it's an isothermal change, then that's the equation that you use. P1V1 is equal to P2V2. But if it's an adiabatic change, then you got to use PV raised to gamma as a constant. And then to find the temperature, use this equation, another equation for an adiabatic change. That's work done during an isothermal change. Negative because work is done on the system, and that's for work done during an adiabatic change. Again, negative. Efficiency of Carnot's engine, .86 or 86%, but the actual efficiency is only 75% of that, so it's 0.65. Well, obviously I'm using different numbers, so I'm having to change the answers. But whatever the numbers are, just understand the concept. That was supposed to be in joules. So that's in joules, okay. Yeah, because I changed it before now. So you get QH and then find the heat exhausted or rejected to the cold object. Number 6. That's the power. Work done per second. I've changed kilocalories into joules. gives an efficiency of 15%. And you get the temperature of the cooler sink, okay, where heat is rejected to. It's number 7. Efficiency has got to be changed from percentage into a decimal before you plug it into the equation. Gives you 592.6 Kelvin. So you can use that to find the new temperature of the hot source if you want to step up the efficiency to 0.35. (911.6 Kelvin). COP of a refrigerator and you get 259.9. Well, density of water is 1000 kilogram per meter cube. So 1 meter cube of water has a mass of 1000 kilogram. That's the latent heat of ice. You get the change in entropy of that process. And then the second one, that is the specific heat of ice, 2100, because you're heating ice from 263 to 273. Okay, so that's for, all right, rather you're going back, so freezing and then cooling ice from 273 to 263, I mean. And both cases it's negative because heat is going out of the system, therefore the entropy decreases, and then you find the total change in entropy. Whenever you mix a hot object with a cold one, heat lost is equal to heat gained. Heat lost by the hot object is equal to heat gained by the cold object. And you always got to remember to put the higher temperature, take away the lower. That helps you calculate the equilibrium temperature. And then separately find the change in entropy, first of aluminum, mass times its specific heat times change. Oh, the T is 24.5, so we've already calculated that. And then find the gain in entropy of water. So that's mass, specific heat of water times the change. and then take the net change in entropy. All right, thank you and good luck.